Welcome back for our last section in series convergence tests. So we're not done with chapter 9 yet, but we're going to wrap up our tests for convergence. And so if you kind of give a nice recap for a second of all of the different convergence tests we've talked about, we introduced what a series was, we adding up all the terms of a sequence. We came up first with this idea that, well, if the sequence terms aren't going to zero, then you must diverge, right? It's not going to converge. And then, well, what happens other than that, right? What if the sequence terms do go to zero? Will it converge? Not necessarily. And so we have to determine, how do we know whether or not it converges or diverges? And we have two special types of series we looked at, telescoping and geometric. Those were the first two we looked at, because in those cases, we could actually find formulas for the partial sums and find the sum of the series, or get a way to figure it out using the standard way to do it, the canonical way, if you will. But in most cases, you can't find a formula for the partial sums. It's not that easy. And so is there a way to get around that and try to test for convergence without having to write out the partial sums? And yes, there is. And that's where we introduce all of our tests. We talked about the integral test. And from that, we get p-series as well, another special type of series. We looked at comparison of series, right? Looking at, well, it's not a special type of series, but it's similar to one that I understand. And so we run comparison tests. We also talked about alternating series, right? Series in which we've introduced negative terms. And those are a special type, right? We've alternated sign, positive, negative, and got some results there as well. Convergence condition. Unfortunately, in that case, we don't have a divergence condition. And then what we're going to do is we're going to wrap it up today with talking about mean ratio and root tests. Now, these tests are tests for absolute convergence. And so the big thing about these tests, you'll notice, is that you're always going to be taking the absolute value of your sequence in the test that you're doing. And in doing so, if you've had any negative terms, they've all now become positive. And so we're considering, okay, what about the convergence if everything's positive? And we're going to get conditions for absolute convergence. We'll also get a condition for divergence. And unfortunately, since we've made everything positive, there is going to be a scenario where we might be inconclusive because we might know something about the absolute value of the terms, but moving back to the series itself, we might not know. Okay? And so we're going to look at the ratio and root tests. They're often paired together, and that's because they have very similar conditions for convergence and divergence. And so the ratio test says given a series. Now it doesn't have to be positive, you have negative terms, you could be alternating, whatever series. As long as you don't have any zero terms in your sequence. You're never going to add zero in. And you'll see why in a second because of the way the test works. And so you consider the limit of the ratio of consecutive terms in the sequence. an plus 1 over an. So a2 over a1, a3 over a2, a4 over a3, so on and so forth as n goes off to infinity. And you're taking the value of those ratios. So look, we're making everything positive. And we're going to take the limit of that ratio of consecutive terms in my sequence and see what we get. We get some limit L. That limit does not have to be finite. I don't say L has to be finite or positive. L can be anything. It will be, worst case, positive, right? You made everything positive to begin with. And so the smallest it would be 0. But limit could be 0 to infinity. Any number could turn up. And it turns out that as long as L is less than 1, it'll be between 0 and 1. And so as long as you get a value for L less than 1, the series converges absolutely. So it tells you something about the series. If this limit is greater than 1, if you get an answer bigger than 1, then the series will diverge. The sum will blow up. However, in this case, there is one scenario that you do not want to get, and that is if L actually equals 1. If L equals 1, this test is inconclusive. That means you do not have an answer, and so you would have to do one of our other testing, integral tests, comparison tests, alternating series tests, right? You have to go a different way about it if you got 1 as your answer. So you hope that you did all this work and you get something besides 1, so that way you can get an answer. So as long as you get L bigger or smaller than 1, you'll have an answer, either converge or diverge. So notice we have both conditions here now. And really, we just don't want to get the number 1. Now, why does this somewhat make sense? I'm just going to intuitively explain this for a second. We're not going to waste time with the proofs right now. But understand that when we take ratios of consecutive terms, if the answer is less than 1, what does that tell me about this ratio of terms? Well, it tells me that an must be bigger than an plus 1. Right, this ratio is getting to a number smaller than 1. Smaller than 1 implies that the denominator is bigger than the numerator in terms of a fraction. So an is bigger than an plus 1. Well, an plus 1 is next term, so that means an plus 1 is smaller than an. So this means in some way it's telling us something about the decreasing nature of the sequence. And if you get a number less than 1, it tells you in the sense that it decreases fast enough. It tells you something about it decreasing. The terms in the sequence are getting smaller, and they are getting smaller fast enough to make you converge. If you get a value bigger than 1, well, that means the numerator is larger than the denominator in general, or you're approaching a number bigger than 1. And what that means at infinity is that the next term is larger than the one before it, and so that means the numbers are just getting larger, they're blowing up, and so that tells me something about the sum of this series. I'm going to be adding larger and larger numbers in a sense, and so then it would make sense that they would diverge. Now, of course, I'm not actually proving this, I'm just kind of conceptually giving you an understanding of why these conditions somewhat make sense. If L equals 1, we don't really know how the consecutive terms compare in a sense, right? The limit's 1. They're the same. Now, are they getting close to 0 the same, or are they going to something else the same? We're not quite sure, and so that's why it becomes inconclusive. Now, when does this series test become useful? Well, it's great because if you have negative terms and you don't like them, you can make them all positive. Absolute value comes into play. Where else is it useful? It's good for tests for series involving factorials. We never really talked about series involving factorials yet because we really couldn't understand them. We don't have a way to deal with them, right? You can't integrate factorials, right? You can't use the integral test. They're not similar to a special type of series. They're not alternating, and so what do we do with them? Well, this is a great test for those. Why? Because when we learned factorials back in sequences, we learned that when you have a factorial over another factorial, you oftentimes get simplification. And that's why this test becomes useful, because you may be able to get a nice limit. So it's great for factorials and also nth powers. We'll get nice cancellation with nth powers as well. And so that's where this test becomes useful. And so let's just get some practice. We'll have another video in this section that will do some additional examples, but let's just get some initial practice using this ratio test. Let's get used to the idea and how it works. And so we're going to take the limit as n goes to infinity. Take the value of the ratio of consecutive terms. So an on my sequence itself is in the denominator. The n plus 1th term will go in the numerator. So that means replacing n with n plus 1. Be careful, it's not n factorial plus 1, it's n plus 1 factorial. You're replacing n with n plus 1. You're not just adding 1 to things. And we're taking the absolute value of that, the ratio of those terms, and we see what happens, what simplifies. In this case, fractions over fractions, let's go ahead and multiply by the reciprocal to kind of clean it up. Times reciprocal of the denominator. And then we see some nice cancellation that happens. Let's look at the nth powers first. You have 5 to the n plus 1 over 5 to the n. Multiplication is commutative, right? So we can switch these around. So we can put the exponential here, the factorial here, so it doesn't matter. We have 5 to the n plus 1 over 5 to the n. Remember what exponentiation means? It just means you're multiplying the same number over and over again a certain number of times. Like 5 cubed is 5 times 5 times 5. So 5 to the n plus 1 is 5 times 5 times 5, n plus 1 times. 5 to the n is 5 times 5 times 5, n times. And so it turns out that the numerator has 1 extra 5. 1 extra times 5. And so I can reduce this to a single 5 now in the numerator. Well, what about the factorials? Well, in the same way, remember how factorials work. Those are consecutive multiplications of starting at 1 up to n. So this is 1 times 2 times 3 times 4, dot, 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 all the way up to n. This is also 1 times 2 times 3 times 4, except I don't stop at n, I stop at n plus 1. So actually, this factorial goes one natural number further to n plus 1. This one stops at n, this one goes to the next one. It's like, if this factorial stopped at 7, this one would stop at 8. If this factorial stopped at 10, this would be at 11. And so what's going to happen here is similar. We're going to cancel those factorials, and all we're going to be left with is an n plus 1 in the denominator. That last term of the bottom factorial that didn't cancel. And then remember, we need the absolute value of this. Now, the absolute value, I don't necessarily need to write at this point because n is positive, right? N starts at 1, 5 is positive, so absolute value doesn't do much for me. And then we're going to take the limit as n goes off to infinity. Well, in this case, we have the numerator fixed. The denominator has the n. That's what's going to blow up. I can write this out as 5 over infinity, but that's not indeterminate. That's 0. Right? The bottom's blowing up while the numerator is fixed. This fraction is going to 0. Now, what's important about that is, look here. We got an answer. We got L. L is 0. 0 is less than 1. And so that tells me this series converges. Absolutely. It converges, absolutely. If I got a limit here and it was a number bigger than 1 or even infinity, then this series would have diverged. If I would have got 1, I would have been a little upset because now I'd have to do something else because I would have inconclusive. Okay, so let's try again. Let's do this one as well. So the limit as n goes to infinity, the ratio of consecutive terms, so the n plus 1th term in the numerator, just always be careful how you write it. Make sure you're actually replacing n with n plus 1 everywhere, not just adding 1. So it looks something like this. Of course, we'll multiply by the reciprocal. We have a fraction inside of a fraction. We actually don't need the absolute values. Because we notice that everything is positive already. The exponential, these are all positive. N is positive because it starts at 1. N plus 1 is then, of course, positive as well. And so initially we have the absolute values, but understand that we don't need them in this case. If I had like an alternating piece here, a -1 at the end, then it would matter. But when I take the absolute value, it would actually disappear. All right, so we have this multiplication. And again, just like the last one, we have some simplification. We have 4 to the n plus 1 over 4 to the n. And so that reduces to a single 4 in the numerator. We have a 3 to the n plus 1 in the denominator. That simplifies to a single 3 in the denominator. And then we want to be careful. We cannot cancel the n or the n plus 1s. So we get 4n here. And then we get 3 times n plus 1 in the denominator. So we get 4 in the numerator with an n. We get a 3 in the denominator with an n plus 1 still. There's nothing left to simplify there. We take the limit as n goes off to infinity. Now, there's different ways to evaluate this limit. We need to be careful. This is actually infinity over infinity at this point. This is an indeterminate. This is not an answer. But this is a special indeterminate. If you remember L'Hopital's rule, we can evaluate this using L'Hopital's rule. This is an indeterminate form in which I can write now this. I'm assuming that we're modeling this by a continuous function. We can take the derivative of the numerator, assuming this is like 4x over 3x plus 3, or 3 times x plus 1. And if I do that in my head, then I realize, okay, well, that's okay to do. I can take the derivative of the numerator, the derivative of the denominator, and that limit's going to be the same as this limit. And now we have the limit of a constant, and so our answer is 4/3. Now, 4/3 is not my answer. 4/3 tells me what my answer is. So if we look here, I got 4/3. 4/3 is bigger than 1. Close to 1, but bigger than it. And that tells me that this series now diverges. This series diverges. So it doesn't converge. It blows up. And so we have the ratio test. We'll do additional examples in another video. This is just kind of a warm-up to get used to this idea of how it works. And what I want to do now is introduce the other test in this section, which is what we call the root test. Now, the root test is very similar to the ratio test. You'll notice very similar conditions, just a different type of limit to take. This one says given a series consider the limit. Instead of now the ratio of consecutive terms, you're taking the nth root of the absolute value of my sequence. You're going to take that limit and consider what you get for that limit, L. Again, if L is less than 1, the series converges absolutely. If it's bigger than 1, the series diverges, and if equal 1 is inconclusive. So very similar test to the ratio test, that's why they're often paired together. This test is more useful for just nth powers. If everything's raised to the nth power, this is great. Of course, we see why, because you're going to take the nth root of it. If you take the nth root of an nth power, they cancel. Like the square root of something squared, the cube root of something cubed. And so they cancel, and so if I have everything raised to an nth power, it's kind of what you see in these examples, the root test is definitely the way to go. This test would not be useful on factorials. Factorials are great with ratios. Factorials are not great with roots. I would not know how to take the nth root of n factorial. And so let's run through these examples. And let's use the root test. So I take the nth root of my sequence, the absolute value of my sequence. Notice everything's positive here, so I don't need to worry about the absolute value. But when I take the nth root of that to the nth power, they actually cancel. And so the limit that I end up needing to take is a nice limit, kind of similar to the last one. 2n plus 1 over 3n plus 2. The nth root and nth power cancel, and the absolute value doesn't do anything. And just like the last one, we can use L'Hopital's rule. We can do all sorts of things. I'll do the algebra shortcut that you learned in algebra with horizontal asymptotes, and that's to factor out that n. So that you can cancel them. If I factor out the n for the numerator and denominator to cancel them, now I'm left with 2 in the numerator, 3 in the denominator, and these fractions. But when I take the limit as n goes off to infinity, both of these fractions go to 0. And so my answer will be 2 plus 0 over 3 plus 0, or 2/3. Now again, 2/3 is not my answer. 2/3 tells me my answer. I look at 2/3 and I say, oh, I got an answer. My answer is less than 1. And so that tells me that this series converges. Converges absolutely. If we got a number bigger than 1, we would say diverge. If we got equals 1, we'd have to try something else. So let's try this one. Nth root of the absolute value. Now the absolute value becomes important because of that -1 to the n. And we take this limit. Now when I take the absolute value, it becomes important, but now that -1 to the n becomes 1, right? Everything becomes positive, so actually this just goes away with the absolute value. And so now I will use the absolute value to now rewrite it as just this. That -1 to the n, when I take the absolute value, makes everything 1 now, right? Because the only thing that this does is -1, 1, -1, 1, -1, 1, but now everything's 1 now. So it's all 1 in the numerator, no -1s anymore. And I'm taking this limit. Now, roots do split up over numerators and denominators. The nth root of 1 is, of course, 1. The nth root of n to the n now is just n, right? The nth power and the nth root cancel, giving me this. We take this limit and we get 0. Now again, 0 is not my answer. We look at my answer, we say, okay, we got 0. 0 is less than 1, and so that tells me this series converges absolutely. So these are very nice tests to use for nth powers or n factorials, even if you have negative terms or alternating. They're nice tests to use, assuming that you can take ratios of consecutive terms, assuming that we can evaluate nth roots of things, of objects. And so in the next video, we'll get some additional examples where we have to be a little bit more careful and maybe they're a little bit more involved, okay? And so in the next video, we'll do a couple examples, again, illustrating the ratio and root test in practice with some additional work to be done.